In this video, we're going to use double integration with polar coordinates to work out this region. So in Cartesian, it's nice and simple. You're moving in the x direction. You're moving in the x direction. You're moving in the x direction from 0 to 4. From 0 to 4. And in terms of the y, you're scanning from 0 to 3. You're scanning from 0 to 3. And we've done this before. It turns out that the area is 12 as expected. But now I'm going to illustrate that you can do the same thing using polar coordinates. So it's much more tedious using polar coordinates for this scenario where you have a rectangle. But the aim of this video is to give you an insight of how polar coordinates work. So in Cartesian it's nice and simple. You're just doing this. But in polar coordinates you have to scan. Remember, polar coordinates scans the angle from an angle of 0 to an angle of 90 degrees, which is pi over 2. So really you need to scan like this. You need to know this radius as you're scanning through this region. You always need to know the radius. You need to know this radius as you're scanning through this whole thing here. You're scanning through this whole thing here. So to convert from Cartesian to polar, you need to change this into r dr d theta, and I've already done an explanation as to why this is the case. So now we need to establish from the radius of what to what, from an angle of what to what. But the thing is, in order for us to evaluate this in polar coordinates, we need to cut up this region into two different regions. So we need to cut this up like this, because as you're scanning through this, hang on, because if you look at this, we need to know the radius from the radius of what to a radius of what. Here you're moving from a radius of 0 to the radius of the vertical line. The radius here, what is this radius here as you're scanning through this whole thing here? So you can see that we're moving from a radius of 0 to the vertical line. But then for this one here, we need to move from the radius of 0 to the horizontal line. The radius of 0 to a horizontal line. The radius of 0 to the horizontal line. So we need to know for given angle theta, no matter what this angle is, you have to know the radius. But the thing is, this radius here is for the vertical line, but then this region here is talking about the horizontal line. So for given angle, you must be able to work out the radius. So hang on. So when we cut this up, this region here will be represented by this integral, and this region here will be represented by this double integral. But we need to be able to work out the radius for any given angle. So imagine this is, let's say in degrees, let's say this is 29 degrees. If this is 29 degrees, what is this radius here? If this is, let's say if this here is 34 degrees, what is this radius here? What is this radius here? So for given theta, we have to be able to work out the radius. For a given angle here, we have to know this radius. So to work out the radius for a given angle, well, let's have a look at this triangle here, which is this one here. So we know that this is always 4. This is always 4. For a given angle here, we can work out the radius. The radius is given by this. So so now we are integrating. Hang on. For this triangle here, which is this one here, and this one here would be this one here. For the first triangle here, we are integrating from a radius of 0. So you start at 0 and then you stop at the vertical line. So for a given angle here, we're actually integrating from r equals 0 to r equals 4 secant theta. So 4 secant theta. And so we're actually doing this. Hang on, we're actually doing this. From a radius of 0 to a radius of 4 secant theta. From an angle of 0 to a radius of 0 to a radius of 4 secant theta. So the first part would be given by this. From an angle, the radius from a radius of 0 to a radius of 4 secant theta, and we're scanning from an angle of 0 to an angle of this angle here, whatever this may be. Well, if you look at this triangle, is 4, 3. What is this angle here? Because we're scanning from an angle of 0 to an angle of here. Well, this angle here is given by inverse tan 3 over 4. So we're scanning from an angle of 0 to an angle of inverse tan 3 over 4. And now we need to consider the second double integral. So looking at the second double integral, which is this region here, we need to do this now. From a radius of 0 to this radius here, which is this horizontal line. So from here to the horizontal line, from here to the horizontal line. So looking at this, let's say looking at this triangle here, that would then be this thing here. Hang on. That would then be this thing here. So for a given angle here, we have to have the ability to work out the radius. So as you're scanning through like this, as you're scanning through like this, given this angle here, you must be able to work out this radius. So as the angle increases, for any given angle here, you have to have the ability to work out the radius. So for any given angle, we need to know the radius. And it turns out that the radius is given by this. So really you're integrating, you're integrating from a radius of 0 to this radius here. So let me illustrate. Let me illustrate. So you're integrating from an angle of inverse tan 3 over 4. So you're actually doing this. Radius of 0 to this radius here, to the horizontal line. Radius of 0 to the horizontal line, to the horizontal line, to the horizontal line. From an angle of this to an angle of pi over 2. Okay, so bear that in mind. So for the second region, we need to integrate it from a radius of 0 to this radius here, and we're scanning from this angle to 90 degrees. So the whole area is given by the combination of these two double integrals. Okay, so now integrate this with respect to r first. So we're trying to resolve this inner integral here, and later on we're going to resolve this inner integral here. So when you integrate this with respect to r, that will then give you this, from 0 to whatever here, from 0 to whatever here. And then for this one here, integrate this, that will then give us this, from 0 to 3 cosecant, from 0 to 3 cosecant theta. So from 0 to 3 cosecant theta. So we're integrating it. So well, anyway, integrate this. That will then give you this thing here, and then let me think. How? Hang on. Let me think. So this line here is exactly the same as this line here. So really, the purpose of this line here, the reason why I put it in there, is to confuse you guys. So from here, you would jump to here. Okay. So we would put this into here, and then put this into here. So that will then give us this thing here. Because, hang on, so I confused myself. Hang on, bear with me. So we are currently here at the moment. So we would put this into here. So when you square it, it will give you 16 secant squared theta over 2. And then you take away, and when you put this into here, it would be 0. Well, if you tidy this up, this becomes 8 secant squared. And the same goes over here. When you put this into here, it will be 9 cosecant squared theta over 2, and then you take away, now put the 0 into here, that would be 0. So this thing here becomes this. So we are now currently at this stage here. So hang on. So now this is a constant. Let's take it out here. And when you integrate this with respect to theta, it would then be tan theta from 0 to this angle here, from 0 to this angle here. And when you integrate this, and if we've done this in calculus too, so when you integrate this, it becomes this. If you can't remember this, then look this up. Well, this here is a constant. Let's take it out here. So that will then give us this. And now, when you put this into here, into the when you put this angle into this angle here, it will be tan inverse tan of 3 over 4. So you're tanning an inverse, so all that's left is 3 over 4. And for this one here, when you put this into here, it will be 0, and then you take away a minus. Hang on, let me do this. Put this into here, that will then give you minus cot pi over 2, and then you minus, and then you put this into here, so that would be minus a minus here, so that would be a positive cot, and then you would put this angle in there, so cot inverse tan 3 over 4. That would then, well, this thing here would be 0. Take my word for it, it's 0. If you think about it, it would be 0. Anyway, cot pi over 2 will be 0, and then this thing here is this thing here. So now we just got to resolve. We've just got to resolve this ugly thing here. What does it mean to have cotangent of a tangent of an inverse tangent of this thing here? So your eyes should zoom into this bit here. Create a triangle where this will be true. Well, if you create a triangle where it's 3 and 4, so this block here represents the angle here. So we want cot. Cot is, well, this is tan. Cot is the other way around. Cot is this thing here. So cot would be 4 over 3. So cot would be 4 over 3. Well, what I'm trying to say is that this whole ugly thing here turns out to be 4 over 3. And this is 9 over 2, 9 over 2. Multiply this out, that will then give you 6. So the area is 12, as expected. The whole point of this video is just to illustrate to you and give you an insight of how polar coordinates work, even when you're working with a rectangle of 4, 3. Okay?